Hi, my name is Miss Townsend and I love math. Welcome to Math with Townsend. This is a video for calculus students where we're going to examine the quotient rule for taking derivatives and do a couple examples together. So, first of all, let's look at questions involving functions that have quotients. Here's one. So I have a function f at x equals 3x squared plus 4x divided by 2. So that is a quotient. But it's definitely not a question where we would use the quotient rule because the denominator is not a function. The denominator is just a number. So the way that we would approach this is we would take that divide by 2 statement and we would separate the numerator into two different fractions, both of them divided by 2. So let me show you that. So we would say that this is 3 over 2 x squared plus 4 over 2x. So the simplest and nicest way to take the derivative is by having this little power package where you have a coefficient, an exponent, and a variable. Here's another power package. Obviously, I would reduce the fraction 4 over 2. But that's what you would do if you have a divisor that is just a coefficient or a number like that. So from here, I wouldn't use the quotient rule. I would just do classic, good old-fashioned power rule derivatives. So let's look at the next example. So here's a function that is technically a quotient. But again, I wouldn't use the quotient rule here because the denominator, even though it's a function because there's an x, but it is a monomial. And because it's a monomial, we can do basically exactly what we did in the other example, which is separate this into two distinct fractions that have the same denominator. So I would rewrite this as 3x squared divided by 2x plus 4x over 2x. And then, of course, I would simplify this before I took any derivatives. This would be 3 over 2 times x because x squared divided by x, that's just x. And this one's even nicer, that's just plus 2. So using the quotient rule on this instead of rewriting it would be an awful long process for no good reason, because as soon as you rewrite this function, the derivative is right there in your face because this is just 3 over 2 plus 0, so that's kind of nice. So when do you need the quotient rule? Well, here's an example of when you need the quotient rule. So I have in the denominator, I don't have a monomial. I have a binomial or any polynomial beyond that. So I can't just split this nicely and then simplify the top and the bottom the way we just did. So this is a question where the quotient rule becomes useful. So I do want to point out that you could, if you wanted to, and I'm not sure why you would, but some people do, you could actually completely avoid the quotient rule by rewriting this as a product rule where the denominator function is written as a regular non-denominator function with that negative exponent. So, you can go through your entire life taking derivatives and never actually using the product rule, never actually using the quotient rule if you did this. And like I said, some people do that, but I want to show you the quotient rule. And I do think that some of the math is easier with the quotient rule. Not all of it, but some of it is. So let's have a look at what the quotient rule is. Boom, 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 boom. There we go. So the quotient rule says if you have a function that is the quotient, so a dividing one function by another function, and again, I would add here, ideally, you only use it if the bottom is a binomial or more terms. So, you tend to not use it if you don't need it, but you would need it if the denominator was a binomial or something more complicated. Then, if that's what you have, then the derivative is, so here it is right in front of you. So it's the derivative of the top function times the bottom function minus the derivative of the bottom function times the top function. And then we have to divide by the bottom function squared. So you can see that the numerator, what's on top, looks a lot like the product rule, except for there's a subtraction sign. And in the denominator, we sort of leave the denominator the way it is in the original function, but we have to square it now. So let's put that to use and take the derivative of, hold on, this function that we had over here. So let me give myself a little more room here. I'm going to go down on my screen. I do not edit my videos because I have no time for that, or much skill, to be honest. I haven't really tried. Okay, so we need to take the derivative. So as a reminder, we have the top function looks like this, and the bottom function looks like this. So we need to do the product rule. And neither of those are very complicated derivatives, so we'll just do it directly. That's a small case f. So derivative of the top. So the top function is a nice polynomial, so the derivative of that would be 6x plus 4. Derivative of the top times the bottom minus derivative of the bottom. So the bottom function, the derivative is just 2 times the top. And then I need to divide by the bottom squared. So that's the derivative in its most ugly, unpleasant looking form. And so again, you can see that what we have is, this is the derivative of the top function, this is the top function. This is the bottom function, and this is the derivative of the bottom function. And of course, there's the bottom function squared. So we do want to try to clean it up. So obviously, we're going to look at the numerator. I don't want to have to expand the denominator because that's generally not helpful in cleaning up or simplifying. But on top, there's a possibility of something good happening, because if I multiply this bracket times this bracket, I'm going to have an x squared expression. And over here, I'm going to have an x squared expression. So I should be able to collect like terms and then maybe factor again. I don't know. Let's see what happens. I'm excited. So I'm going to multiply those two together. So I'm going to do FOIL. I don't need to go through every step. You're here. This is calculus. So 6x times 2x plus 6x times 1 plus 4 times 2x plus 4 times 1. And then over here, negative 2 multiplied into that bracket is negative 6x squared minus 8x. And then I can't forget that there is a denominator. Even though I'm not doing anything with it, it would be wrong to stop writing it. So what happens to that numerator? If I collect like terms, I get 6x squared minus 2x plus 4. So let me just double check that. 6x squared. And then I've got, oh, good thing I'm checking it, because I was wrong. This is 6x plus 8x minus 8x. So this is plus 6x, and then plus 4. That is divided by 2x plus 1. So obviously, I'm going to common factor, and then I'll see if I can factor that trinomial. So I'll factor a 2 out, and then boom. And now I'm going to try to factor that trinomial. Are there two numbers that multiply to give 6 and add to give 3? No, because 6 is either 1 times 6 or 2 times 3. This would add to 7, this would add to 5, so it's not possible to factor further. And that is the derivative of that function. So I'm going to do a few more examples. Let me just double check that I'm actually recording. Oh, good.